In this video, we want to create a new script that allows the character to decide which direction to move. We will call this script character movement. The same technique will eventually allow us to add other behaviors to our character. Let's open the script in the editor. This component will also include another timer setup. Let's create the timing variables and method first. In this case, we'll have one integer called decision clock that will be the timer counting up, and then we'll have another integer called decision time, which will be the time that it's counting up to. We now create a method named tick to represent one increment of the decision timer. In this method, we set up the same kind of timer we used in the character animator script. We increment the decision clock by 1 every single tick, and then we check to see if the decision clock has reached the decision time. If we hit the decision time, then we first reset the decision clock. And now we need a vector to hold the direction our character decides to face. We'll initialize this vector to the 0 vector. And we also need a method that generates a new direction. In this method, we instantiate a new instance of the random system class. This will allow us to generate random integers that we'll use as the components of a random direction. Now we'll define a new vector 3, which will be this new direction that we're trying to generate. And we'll use this next function in the random class in order to pick a number that is -1, 0, or 1. We'll do this for both the x and y components, and that will give us one of the 8 directions. We're also defining a small conversion method to transform the Cartesian vector into the isometric projection that we need to move the character around on our isometric map. If we didn't do this, we would get the directions for the character to move on a top-down map, as opposed to the isometric directions we want. All of this code is available in the repository if you want to take a closer look. But understanding the math in this conversion function isn't particularly important for our purposes. We can now finish the getDirection method by returning the new direction, but transforming it with this toIso conversion method that we just created. We also normalize the direction so that the character walks in the same speed in each direction. We decide to change the name of this variable to new direction so that it more clearly expresses the purpose of the variable. If we return to the tick method, we can now finish the decision-making part of the code. After we reset the timer, we can get a new direction from our getDirection method. For the next step, we need to add one more method to the character animator component. This method will be called setAnimation, and it takes a direction vector as its only argument. This method will decide which animation to play based on the direction the character is moving and the current animation type. If the direction is a 0 vector, meaning the character isn't going to be moving at all, then we set the animation to be the idle version of the current walking animation. So if the current animation type is walk up when the character is just about to stop moving, then we will set the current animation type to idle up. And we will do this using the playAnimation method that we created earlier. We will now do the same thing for the other animation types. Now we'll handle the cases where the player will be moving in one of the directions. These are much simpler checks. We simply play the animation associated with that direction. The art for the character that we're using has 4 directions. If you have a character that has 8 directions and you want them to move in all of those directions on the tile map, you can set up more checks in this method to make sure that all of the animations are played correctly. There's a lot of room for exploration and customization here in this step, and once you add in more animation types, the transitions between them will become even more complicated. Unity actually does have an animation system that can help handle some of this complexity, and we may explore that system in later videos. Let's return to our character movement script. We need a reference to the character animator component in this script. Just like the components that Unity provides, we can also retrieve our custom components using the getComponent method, as long as we've attached them to the game object. We can now use this reference to the animator to complete our tick method. We will pass our new direction to the setAnimation method that we created earlier. The character is now choosing directions and setting animations correctly. The only thing we have left to do is to actually make the character move around on the screen. Since we are going to apply physics to our scene, we're going to need to attach a rigid body 2D to our character. So we'll define a variable to hold a reference to this component. And we will assign this reference in the start method as usual. To move the character, we'll define a new method called move. This method will be called in the update function right after tick. We'll now define the move method. To move the character, we're going to set the velocity of the rigid body 2D component. This script will need one more variable that will hold the speed of the character. When we go back to Unity and reload the script, we notice that we've actually hidden an inherited member of our class. The game object has a built-in reference to its own rigid body, and it is also called rigid body. It appears that this reference is actually a deprecated feature, but hiding it will still cause this warning. I actually intended to use the camel case for this variable, which will fix this problem. We now need to attach the rigid body 2D component to our character. We also need to freeze the rotation around the Z-axis. This is so that when the player runs into other objects in the scene, the physics engine doesn't try to rotate the character. I made a mistake at the end of the setAnimation function that we have to correct before moving on. The last animation was supposed to be walk down. Okay, let's run the game and see how this is working. Nice! The character might be moving a little slowly, but it does appear to be doing everything correctly. And you can see here they move behind the wall. Alright, in the next video we will enable collisions between the character and the map. We will be adding a new tile map to our grid. This will allow us to separate all of our collision on the tile map from the actual tiles that are on the map. This means that we'll not only be able to make the walls solid, we'll also be able to make invisible barriers around the tile map as well. Using the method in this video, you can add a number of different behaviors to your character. We'll be expanding on this technique on this channel, but we'd also like to see where you take this project.